My scientific journey, like many scientists, has not been a linear one. I started at the University of Sydney. I did my undergraduate and PhD degrees there, and I trained as a biochemist and structural biologist, and went and did a postdoc in Oxford and came back and joined the faculty at the University of Sydney. And my interest was in cancer, in particular transcription factors that were involved in cancer and how we might be able to inhibit them. And I got completely sidetracked by a colleague who suggested I might work on a venom toxin, and that completely changed the path of my career. The reason I got interested in venoms in the first place was the idea that spiders are the best insect killers on the planet. Surely their venoms would be a good place to find more environmentally friendly insecticides. So we started looking in spider venoms to find compounds that were not just insecticidal but were harmless to humans, but also beneficial insects like bees. And we managed to find some really interesting molecules, and that led us to found a company called Vestron Corporation, now based in Michigan, United States, and they've developed the first venom-derived insecticides that turn out to be really very environmentally friendly and even safe for bees. Our work on venom-derived insecticides made us realise that venoms were super complicated. I thought they might contain a few compounds, maybe a dozen, but it turns out that many of them contained hundreds to thousands of molecules, and what we realised that some of them had properties that may make them useful as therapeutics. And so we switched gears and started looking at venoms as a potential source of human therapeutics. Yeah, we got really interested in jellyfish venom because they proved really hard to study. The venom toxins themselves are rather unstable. They've proved intractable, say, to classical proteomics and transcriptomics. So we've turned to the genome to see if we can use the genome to understand, one, what is the toxin repertoire of these two jellyfish, and why do they cause completely different envenomation syndromes, even though they both are potentially deadly. Yeah, the box jellyfish and Irukandji jellyfish are really fascinating animals. They're both deadly, but they cause completely different symptoms and kill people in different ways, and we just don't understand why they're different and how they're different. And their venoms are very difficult to work with, they're very unstable, so it's been difficult to work out what the deadly toxins are. And so we've turned to genomics, and we're hoping that the genomes of these animals will tell us what the deadly components are and how they differ between the two animals, because we know they must be different. These jellyfish can kill really quickly, so the box jellyfish can kill a person in just a few minutes. So we think antivenoms are probably not going to be the answer because it will take too long to get the person to hospital and give them antivenom. We're hoping the genome will tell us what the deadly toxins are so we can develop some therapeutics instead that we could give to the person prior to taking them to hospital to give them some antivenom. Absolutely, we're really passionate about preserving biodiversity, even of the most deadly venomous animals, because these animals play a really important role in their ecosystem. And more than that, even though an animal may be deadly, doesn't mean it can't have life-saving drugs in its venom. And a classic example is there's a deadly Brazilian viper called Bothrops gyrarica, and from that venom of that animal, we got a life-saving hypertensive. And even though that snake has killed a few people, many thousands of lives have been saved from the antihypertensive drug we got out of its venom.